Hi, my name is Yoav Artzi. This is a short talk about our paper, Retrospective Learning from Interaction. This paper will be presented in ACL 2025, and this talk is a short version of what I'll present there. This work was led by my PhD student, Chen. The context for this work is this very common view on LLM lifecycle, where we separate between training and deployment. In training, we're mostly using static data, a lot of raw data for pre-training or expensive annotated data for post-training. In deployment, on the other hand, the data is very different. It's much more dynamic, it's conversational. These interactions create ton of data that is fundamentally different and it does not follow and follows a non-stationary distribution. And largely, there is no learning happening during this deployment stage. However, these interactions that the model participates in during deployments are rich with learning signals. And even more important, they're always on distribution. This creates a lot of opportunities. So, adaptation and personalization, acquiring new knowledge to update the model, and overall reduction in training costs. The gist of this paper is that we can learn from observed conversational behavior in such interactions. And the reason for that is that conversational interactions span multiple turns. This creates opportunities to learn from observed behavior. Model outputs are naturally followed by human responses. These responses are influenced by the model output and its quality. And this creates an observed behavior that captures a very informative learning signal. How does this signal look like? Interlocutors dynamically adjust their behavior based on partner behavior. Speaker utterances or behavior following an interlocutor response encode feedback about the response, even if implicitly. Errors may elicit rephrasing, pivoting, scolding, direct corrections, etc. For example, in this comic strip, Charlie Brown received and decoded feedback about how to lose, and maybe, just maybe, he will do better next time. On the other hand, correct responses elicit very different behavior. They may lead to building on top of what was communicated, or even explicit phrase. In this work, we present an approach called RESPECT, which stands for Learn Retrospectively. It's an approach to autonomously learn from these kind of signals without any annotation or human intervention. It has 3 stages. In the first stage, we deploy the model to interact with users in conversational interactions. We then, in the second stage, retrospect, we use the same model that participated in the interaction to decode feedback based on the follow-up human responses and utterances or behavior about the model actions. This is very different than the conventional use of AI as a judge. The model here does not judge the quality of its own outputs. And as you will see later in our setup, it actually does not have the ability to do that. Instead, it analyzes follow-up human utterances, and from there decodes feedback about the action that preceded them, the model action that preceded them. We then take this feedback and in the last stage convert it into training signals and retrain the model. In this kind of process, there is a very interesting cyclical influence. Training influences deployment, and deployment influences decoded feedback. This raises questions about what are the long-term dynamics. To study that, we deploy this process in a continual learning setup, where we repeat this process again and again in multiple rounds. This allows us to observe long-term trends and also to evaluate the effectiveness of our model. Because as we train at the end of each round, we will observe how much the model improved by deploying it in the next round and observing the model in the wild. So what is inside each stage? First, the interaction scenario. We design a lab scenario to support the research, revealing the critical challenges and the properties of the interaction that we are interested in studying, while at the same time scoping the research challenge, the research and the learning problem to enable research-constrained research in a lab. We introduce multi-ref. Multi-ref is a generalization of the well-studied and reference game scenario, a well-tried workhorse in cognitive science in NLP. There are several key differences between multi-ref and reference game. First, instead of selecting a single target, like we do in traditional reference games, here we select in multi-ref we select a subset of the targets. This has dramatic influence on the solution space. Rather than the solution space being the number of targets that are observed by the participants, it's any possible subset, which means it's a very large combinatorial space. And this naturally lends itself to gradual construction of the solution. So instead of a single-turn interaction, like we see in reference games, we have a multi-turn interaction, expressing all the properties of interaction that we are interested in studying. In our deployment, the model takes the listener role. This is how a multi-ref interaction looks like. We have two participants. The human is always a speaker, and the model is always a listener. They both observe a set of images. These labels are shuffled between their perspectives, so they can't communicate by just pointing to a label. The human gets a set of targets, and their goal is to communicate them to the listener, so the listener selects these targets and now no other images. This interaction starts by the human generating the utterance, a diamond-hand man without legs. In response to this utterance, the model selects image I, which seems appropriate in this case and is also one of the targets, so it is likely a desired behavior. The human continues and says another diamond-hand man. Now the model selects image C, which does not seem like a terrible mistake, but it's not one of the targets, so it's likely an incorrect selection. Indeed, the human responds to this utterance by implicitly correcting the model by refining the previous utterance, hoping that the model deselects C and selects something else. Already these utterances, you can see the very abstract language that we observe in multi-ref, very rich linguistic behavior, and a lot of pragmatic reasoning. In response to this utterance, the model deselects C correctly as appropriate and selects G. Seems like the right selection. This interaction will continue until they run out of turns. This is 10 turns in our case, or the correct subset is selected. So what do we have here? This scenario builds on reference games. It's a classic prototype in cognitive science to study communication and grounding. So we are building here on decades and decades of research and studies in cognitive science and NLP. For our visual stimuli, we use tangram images. We have a very diverse set of tangrams from the kilogram dataset that we released a few years ago. These are abstract shapes. They are very hard and out of distribution for pre-trained LLMs. This means we have a lot of room for improvement, so we can really see the effect of our learning. They also have a very rich and long history in cognitive science, going back 4 decades in research. And that allows us to expect that, and indeed this is what we see in our experiment, that we'll get very diverse description with a lot of abstractions and visual language. And finally, because we are building a complex solution, we have a multi-turn interaction with rich dynamics, with corrections, rephrasing, pivots, all the kind of properties of interaction that we are interested in to take advantage of as our learning signal. Given this kind of interaction, we switch to the second stage of our process, where we retrospectively decode feedback from these past interactions. The hypothesis underlying this work, the most important thing, is that implicit conversational feedback is expressed in a relatively constrained way and a general way that is task independent. So the ability to decode it is potentially acquired mostly during pre-training, and an LLM can decode it even if it is terrible at the task of the interaction. Now, if an LLM can decode this kind of feedback from past interactions to infer a learning signal that it can use effectively, it can bootstrap and autonomously improve simply by interacting with users while completing its task and what it's supposed to do. We take the simplest possible approach to decode this signal, and we use prompting. We design a general, task-agnostic, text-only prompt with minimal design. In our case, the fact that this is a text-only prompt is really important, because this really allows us to control if the model is judging its own actions, the quality of its own actions directly. It cannot do this in this case because the model does not observe the images the participants are referring to. Our prompt is extremely simple. We have a set of instructions, we have the history of the interaction, text only, the model action, and the follow-up utterances from the user, from the human participant. We then ask the code two types of feedback. We either do a freeway feedback, positive, neutral, or negative, or we experiment with a binary feedback, positive and negative. In this example, we ask for positive, neutral, or negative, and the decoded feedback is negative. Given this decoded feedback, in the last stage, we convert it into a training signal. We experiment with free learning methods. Each of them has its own kind of conversion process. We use filtered fine-tuning, where we only keep the examples with positive feedback, and we simply maximize their likelihood. We experiment with reinforcement learning, RL, using in a contextual bandit setting. We convert the feedback to positive and negative rewards and maximize the reward with reinforce. And finally, we use utility maximization with KTO, where we use KTO with positive and negative feedback. So this is the complete process. We deploy, retrospectively decode feedback, and retrain the model, and we repeat this process again and again. For our experiments, we run concurrent, randomized deployments with humans. We vary the feedback decoding, binary versus ternary, and the training methods using the free algorithms I just described. We deploy 6 systems for 3 rounds, and continue with the winner for another 3 rounds to observe longer-term trends. For our model, we use Idefix 2.8b. It was the state-of-the-art multimodal LLM when we conducted these experiments. These are our main results. What we're seeing here is interaction success rate. We're seeing the 6 systems, binary with FFT, ternary with FFT, binary with RL and ternary with RL, and binary with KTO and ternary with KTO. Binary and ternary stand for the feedback with the code, either positive, negative, or positive, neutral, and negative. We also deploy here 2 systems, control and human-human. Human-human interactions are basically at 100% success rate. Within the allocated 10 turns, the humans have sufficient time to correct themselves and complete basically all tasks successfully. Overall, all the learning methods show dramatic improvements and effective learning. The best learning method, and the one we continue with for 6 rounds, is binary FFT, which is the simplest of the 6 methods. Its success rate over 6 rounds at interaction level goes from 31% to 82%. A big question, a confounding factor in this kind of experiments, is how much human adaptation is contributing to the system improvement. So we take the initial model and we deploy it concurrently to the final binary FFT model in a randomized experiment. And what we see that human adaptation is negligible. Performance stays roughly the same, telling us that all the improvements is coming from the system actually improving its reasoning its capabilities. Filtered fine-tuning works best, but overall most of the learning methods work relatively well and differences between them are relatively small. The only difference is KTO, which struggles potentially due to open problems in the repeated optimization that happens throughout this process. Turn-level success rate, which is not visualized here, also improves dramatically from 30% to over 50%. Turn-level success rate is evaluated using separate evaluation task. There are more details in the paper. There's also a lot more analysis in the paper. So if you're interested, I recommend you to give it a look to understand what kind of dynamics happen over time in this process. So thank you very much. I'll point you to the paper here. And this work was led by my PhD student, Chen, together with collaborators Omer, Yiwei, Chen, Gloria, Geng, and Wu, and myself, Yoav Artzi, as the advisor. Thank you.